So let's continue the frequency response, right? So last time I skipped this slide, but now I think it's time to go over step by step, just remind us what we are talking about. I give you a circuit. First, we determine which capacitor will impact the low frequency regime. Those are the big capacitors, right? And so in this part, we try to find out the transfer function. But at this time, we try to ignore the transistor parasitic capacitor, CGD, CGS, CDS, and CDB, and what else? CSB, right? We ignore that. Then we go to higher frequency, at which, thank you, at which so maybe it's good, let me just draw an example circuit so that you understand what I'm talking about. Right, I have this common source amplifier, right? It is biased like this. I have an output, I have the input, right? Maybe a better example is use the one that we had last time. Something like common source with degeneration. Remember this? So what we do is, okay, now we are at low frequency. I don't draw any high frequency capacitor, parasitic capacitor, because they're small and our frequency is small. So 1 over S omega is very large. So it's just like open circuit, right? But this capacitor is fairly big because I add it to my circuit for certain purpose. So I need to include it in my transfer function, right? This is super big. Maybe at DC, if they have effect, right? But in low frequency, maybe 10 hertz or 100 hertz, they kind of get shorter already. But I can still add that in the low frequency analysis. That is the first part. Then let's go to even higher frequency, to the mid band. It is where I want my device to operate. So at this high frequency, these capacitors, they are large. So basically, they are all shorter, right? So in this particular case, this resistor and this capacitor got shorter. It becomes a common source. So at mid-band, this works as a common source instead of a common source with degeneration. But before mid-band, the transfer function is that of a common source with degeneration, right? So that's fine. And then eventually, what do we do? You keep going to higher frequency. And at that time, you not just can ignore this large capacitor, you also need to start adding the parasitic capacitor to it. Right? This is CGS, CGD, CDB, and CSB, right? So I add this to it, and of course I need to do something. What do? Is I merge the capacitor, right? And I omit those that has no role. We did that before. And then we may use the Mueller theorem and then find the poles at this high frequency. So eventually we complete the whole body part of this system. Is that okay? Any questions? So that is what we did last time, right? So last time we have this device. At low frequency, we start with everything except we don't have this high frequency capacitor. Then we try to find the transfer function of this circuit. And again, I know this is common source with degeneration from Vx to Vout. So that's why I just use Vout divided by Vx. I use the common source with degeneration equation. But this is, I put the GM down, right? It should be negative RD times GM divided 1 plus GM times the degeneration impedance, right? So that is this, and then we get this. But however, I'm interested in the transfer function of this whole circuit. So that's why I also need to know what is Vx divided by Vin. And this is just a simple voltage divider, right? Based on this, we find that, well, I have a 0, which is at negative infinity. If I take the log, so this is not accurate. This should be log of omega instead of just log, right? Instead of just omega. So I have a 0 going from negative infinity when I take the, means I'm going from 0 frequency, right? It goes up, eventually hit the first pole, then it flat out, and then I have another 0, then goes up again, and then hits the second pole, then it flat out. And this is the mid-band that I'm interested in. I'm going to operate my device at this gain, which is just GMRD, the common source amplifier. Okay, any questions? And then now we want to go to high frequency, right? So last time we have not covered this. And as I said, we are going to identify the capacitor, contribute by the transistors, right? And then just apply whatever we want. And just a quick question for you, right? At this stage, when I'm doing the high frequency, I said V in equal to Vx. Why? They are coupled, yes, and then they are shorter, yeah, because the impedance due to Ci equals to 1 over J omega times Ci, right? And now you are at high frequency, and Ci is also large. So this one is almost equal to 0, right? So you have 0 impedance, then V in equal to Vx. Right? In this analysis, because we're doing high frequency, right? So let's start with this, right? I have not shorted it yet. And for this circuit, I also add one more resistor to it. This resistor, you can think of wire resistor, or the resistor come from the voltage source. I call it Rs dash, okay? Just to complete the analysis. If you're so good that you have 0 Rs dash, that is fine. Then you just substitute accordingly, right? But usually you do have this. So let's look at the circuit and see how we should deal with this. We are not going to draw the small signal from scratch, right? But we will still do some AC manipulation on this circuit and then add the small capacitor, because now we are very good at this already. So the first thing what I will do is just draw the circuit in this way and see if you agree with me. So from V in, I ground it. And then I have this out as dash. And then I don't have Ci because I say that this is at high frequency. The Ci is shorter. And I have a resistor here, R2. And I also put here R1. I put them to ground. Then I put this to the transistor. Let me still draw RS. Still draw it. And still draw CB, but we need to be careful. And then I have this RD. I put this to ground also, okay? So let's go through this. Why do I do this? First of all, why this is grounded? My goal is to find the poles, right? To find poles. Find the pole. Yes. We are using the fast method, right? To find the pole at node S. One of the rule is what? You need to ground all the independent source, right? So this is ground independent source. Okay. So let's remind ourselves, why do I ground this guy? Isn't that is connected to VDD? Isn't R1 is connected to VDD? What's the reason? It's independent source, but even if it's not independent source, what is another reason? Yeah, We are doing AC analysis, right? So you can say independent source or AC analysis. Is this okay? Right. So when we're So when we are doing the AC analysis, you need to ground it, right? That we have been talking about this, right? So do not make mistake. And then I'm going to do this also. Ground this guy, right? Short it, I short CB. Why I can do this? High frequency. Because 1 over J omega CB is small. Okay? So if I short the CB, which I already told you is nothing new, right? I already told you here that I'm going to short it at high frequency, right? Because this is a large capacitor. And then you may say, what if I cannot short it? Then you did not design a good circuit. You need to increase the size of your CB. Okay? And what if I'm not allowed to make it large? Then it is the limitation of your product. You either don't sell it or find another topology, right? You already hit the engineering limit. Okay, but in this class, we assume it works. And since it works, then CB needs to be shortened. Okay, you have question? Do you have question? Yeah. Huh? Say again? This one? Okay, you know we upload this slide to Canvas, right? Okay, so you can just download. Okay, looks very simple, right? Wasting your time, but everything needs to be clear. Once it is clear, then it will be easy, right? So basically, after this, my circuit becomes very simple. I will just have this one, the whole thing. This whole thing is gone. And this is grounded. Okay? Good. So now I want to find the pole. How do I find the pole? Well, there's no pole for me at this moment, but it's at high frequency. So I know that I have 4 capacitors. C, D, G, or CGD. C, D, B. And then from here, C, S, B. And from here, C, G, S. Is that okay? Just 4 capacitor, right? Put in. Now, very messy, right? How about let's do some transformation before we find the pole? Let me see, do I have space? Yeah. Now say again, you can. Very good. How come CGS doesn't connect it to S, right? Because I already assumed the S is shorter due to this part. Yeah. So you're right, it should be connected to S, but then this is shorter to ground. So let me redraw this and it will be very clear. So I have RS dash in, sorry, let me redraw it. RS dash parallel R1 parallel R2 CGS1. Okay. I'm going to ask you some question later. This is easy, right? This is just run. Thank you. And then CSB, correct? Source to the body, right? RD. This is better. So I'm going to put RD here. RD. And then this part, I have CDB. Okay. Do you agree with what I'm drawing here?
You're missing a CGD.
Very good. He said, I still miss the CGD, right? But what do we want to do? Use mirror effect, right? So this becomes CGD times 1 minus A. This is CGD times 1 minus 1 over A.
So let's say because it's
Okay, the equation is 1 minus A, right? But then what is A? Yes. A is the gain of the midband, right? We need to find out what is A, which is negative GMRD, right? This is absolute value here. So A is negative GMRD, right? How about CSB? Do I need to care about that? 0 to 0. Very good. Sorry for this drawing, huh?
because it's shorted off.
Yeah. RS and CB are in parallel, but now CB is shorted to ground, so RS is also no effect. So this point is basically ground. That's why I put the green line here, right? So we have ground on SB on both sides. That's why it is gone. Yeah. So now we can find the pole. Let's find the pole. P1, what is the P1? Which is X. It's 1 over RC, right? But R is just RS dash parallel R1 parallel R2 times. Let me just call this C in. That is pretty long, so I don't want to copy. Is this okay? And then how about the pole 2? What is that? Okay. You call this C out, so you say it is 1 over RD C out. But what if I include the channel length modulation? What is that? Thank you. RD parallel RO C out. Is this okay? Then we need to complete the body part. Let me see if I have this at the end. Somehow I don't have. Yeah. So let's complete the body plot. So what do we really get from here? Earlier we did the low frequency, and we get this. Maybe I can show you 1 0 1 pole, right? Do you see that? 0 is not 1 0 1 pole 1 0 1 pole, and becomes the midband, right? So you have 1 0 1 pole 1 0 1 pole 1 0 1 pole, which is the midband. You hope that it can go forever, but unfortunately it does not, because now you have this high frequency capacitor. You hit one pole here, and later you hit another pole. And this is, maybe I should not call it P1 because, okay, I did not say that, so I can call it P1. This is P1, and this is P2. Okay, that completes the whole body part. And now you understand why the circuit has limitation. Even at low frequency, it has limitation because you need to bias it. And we remember at low frequency, it works as a common source with degeneration, right? And this is the region, the midband region. This is where you want to use. So you design an audio amplifier, maybe this is 10 hertz, this is 20 or 30 kilohertz. And I don't care what is outside, because my voice does not contain this spectrum outside, right? So any questions? We're done with our first example of body plot without really solving the KCL, KVL. And the more important thing is that you have insight. Even you solve KCL, KVL, the equation are so lengthy. You want to improve something, let's say, hey, can I push the P1 further to the right, but keep the P2 the same? Or only push the P2 further to the right, but keep P1 the same? It's difficult to see. But now it's very clear here. Well, you want to push P2 further to the right, let me reduce C out. Or let me reduce RD. Maybe it works, right? But RD is going to change your gain. Then you know that you push this gun to the right, this is going to go down. Can I afford that? Then now you have insight, right? Okay,